In this video, I'm going to do a summary for all the Year 12 or AS mechanisms for AQA. So the first one we'll look at is the radical substitution mechanism, or free radical substitution mechanism it's sometimes called. And the example I'm going to use is ethane with bromine. So basically we're looking at the reaction between an alkane and a halogen. So this reaction would not take place without some assistance, and that's because the alkane and the halogen are both non-polar molecules. So there's no kind of attraction between the two molecules. So the condition to get this reaction to go is UV, or ultraviolet light. So the first step of the mechanism is what we call initiation. And that's where the UV splits the bromine molecule into two radicals or free radicals. So what we get, the equation basically looks like this. So the bromine molecule is broken and creates two free radicals. And obviously the free radical is represented by that dot there, which represents an unpaired electron. So if I just show you what's happening there, because there's a special term for this type of bond breaking. It's known as homolytic fission. So I'm just going to concentrate on the pair of electrons in the covalent bond that's broken. So if we think about the bromine molecule, we've got a pair of electrons in that covalent bond. The UV breaks the bond in such a way that the pair of electrons in the bond is shared equally, okay? So this bromine on the left gets one electron from the pair, this bromine on the right gets one electron from the pair. So the homo bit is the fact that they both get the same number of electrons from the broken bond, okay? So that bond breaks homolytically. And obviously you can see that when this left-hand one breaks off, it's going to take that unpaired electron with it. So that's why we use the dot there, and likewise for this one here. So these free radicals or radicals are very, very reactive. They've got an unpaired electron, so they desperately want to pair their electron up with something. And so that's how this reaction gets to go. So the second step is known as propagation. And basically these are a pair of steps, so there's always two of these steps. So what we're going to do is we're going to take the ethane molecule, so C2H6, and we're going to take one of those radicals. And what happens is the bromine radical gets the electron by stripping out one of the hydrogens from the alkane molecule. So I always tell students to put the hydrogen halide in first. So you always get an HBr in this case, or hydrogen halide produced, and then the remainder will be the C2H5. Remember, that's lost that hydrogen, and it's also lost the electron that went with the hydrogen. So this is now a radical. So it has an unpaired electron. So we represent the ethyl radical like that. So remember I said this was a pair of steps, so I would call that P1, propagation 1. So the second propagation step, we're going to take this newly formed radical and we're going to react it with some bromine that hasn't been broken or could have reformed. You'll see how that's possible at the end. So what that's going to do is that needs to pair that electron up, so it does that by pulling one of the bromines away and obviously gets the electron to go with it. So that's going to create C2H5Br and a bromine radical. So that's your pair of propagation steps. And then the final step is what we call the termination step. Now, basically, in a termination step, you just take two radicals and pair them up, okay? So there's actually more than one possible termination step in this mechanism. So you could take two bromine radicals So 2 Br dots going to Br2. So that obviously explains why there's some of that present for the second propagation step. We could take these two radicals here, so C2H5 radical and a bromine radical. So that's another way of making the C2H5Br, but this is via a termination step. And then the other possible termination step would be two of these ethyl radicals combining. So 2 C2H5 radicals would combine to give C4H10. So if you were to carry out this reaction, there would be small traces of butane present in your final product, because obviously it's possible to make butane via this termination step. So if you were wanting to make bromoethane as a single pure substance, this method wouldn't be great because of the fact that you can actually get other products formed. Now the other thing to say is that if the halogen is in excess, you'll notice that the second propagation step actually reforms the bromine radical. What that can do is that can start stripping out the next hydrogen from your halogenoalkane that you've got now, and then another pair of propagation steps can happen and you can end up with the dibromo product. And then obviously if there's still more bromine radicals present, you can strip out the next one and so on. So ultimately you could end up with C2Br6, all of the hydrogens stripped out and replaced or substituted by bromine. So I'll just show you the sort of next one in the sequence and then we'll leave this one. So I'll just get rid of these. So this is another reason why this is not such a great method for making a single substance. And that's because further substitutions are possible. So we said that we've made C2H5Br, but the bromine radical is in excess. So that will strip out the next hydrogen, so we get HBr. Remember, I would always put that in first as a reminder that you're going to get HBr in this case. So what's that going to leave us with? It's going to leave us with C2H4Br, but that's now a radical. And then that, so if you remember what happened the last time, so the C2H4Br radical can react with some bromine, the molecule. That's going to take one of the bromines away and the electron, so you're going to get C2H4Br2 and a bromine radical. And so that's how the dibromo product would form. And then obviously, I won't do them all because we would be here all day. That bromine radical and then strip out the next hydrogen from this and you'd set up another pair of propagation steps. So the next mechanism we'll look at is electrophilic addition. There's a few of these we need to look at. So the first one is an alkene, so I'm using ethane in this case, alkenes with halogens. So I'm going to use displayed formula for this one. So let's draw up the ethane. Okay, and we'll draw the chlorine molecule over here for starters. So chlorine is a non-polar molecule because the atoms have identical electronegativities because it's the same atom. But as it approaches the carbon-carbon double bond, you've got a high electron density around the carbon-carbon double bond because of the presence of, remember you've got a sigma bond and a pi bond present. So you've got a high electron density there. So if we bring our chlorine closer to this double bond, what it's going to do is it's going to polarize the molecule and the electron pair in the bond is going to be repelled slightly closer to this chlorine here. So this end of the molecule is slightly negative, this one slightly positive. So because we've got this sort of charge difference now, the pair of electrons in the pi bond, remember they're sitting on the outside of the molecule, they're going to be attracted to this slightly positive chlorine. And so we show that with a curly arrow. Curly arrow shows the movement of a pair of electrons. So I'm just going to rub out the pi, the sort of symbol pi now, and just make a point there. Your curly arrow needs to come from the middle of that bond, okay? So be careful you don't draw it coming from an atom. That's wrong. Okay, it's got to come from the bond, ideally the middle of the bond. Okay, so that's the first thing that happens. So we've now got electron density much closer to this. So what that's going to do is it's going to repel the pair of electrons in this bond that are already sitting closer to this chlorine. They're going to repel them completely onto that chlorine atom there. And what that's going to do is it's going to break this covalent bond here. So the type of bond breaking that's happened here, this is called heterolytic fission. So that's because the pair of electrons in the bond, both of them have been repelled onto this chlorine. So if you think about the pair of electrons that were in the bond, this chlorine's got two of them, both of them. This chlorine hasn't got any of them, so that's a different kind of number. So heterolytic fission, we've got both of the electrons gone onto this atom here. This one doesn't receive any of those from the pair. So if we move on to the product of this part of the mechanism, this is not the final product, it's an intermediate. So we've got two carbons. There's the two hydrogens on this first carbon. That's that sigma bond that hasn't broken. And we've got hydrogens here and here. So we're going to put the chlorine on that carbon there. I mean, it could have gone there, but I've chosen to put it there. Okay. So this carbon here has basically become positively charged. So I need to explain that. So if you think about the pair of electrons that are in this pi bond at the start, one of the electrons belongs to this carbon, one belongs to this one, okay? So when this new covalent bond's formed, that one there, this carbon's effectively lost an electron because it's sitting in this bond now. So that's where that positive charge comes from. So this is called a carbocation. Cations are positively charged, carbo contains carbon. The chlorine has become negatively charged because it has gained an electron. So it already owned one of the electrons in the pair, but it's gained one more. And so I'm going to show that pair of electrons there, and basically the final product is formed by this pair of electrons, negatively charged electrons, being attracted to that positively charged carbon of the carbocation. And a covalent bond is going to form between that carbon and that chlorine. So the final product looks like this. The reason it's called electrophilic addition is because, well, an electrophile is defined as an electron pair acceptor, and so you can see this part of the chlorine molecule is accepting the pair of electrons from the pi bond. So this part of the chlorine is accepting a pair of electrons, so it's electrophile, so electrophilic. Addition, basically because the atoms in the reactants have all combined together, okay? The way of thinking about addition reactions is two reactants become one product. Okay, so the second electrophilic addition mechanism we'll look at is the one between an alkene and a hydrogen halide now. So I've just changed chlorine to HCl, hydrogen chloride. We've got the hydrogen halide here. Now, even if I'd drawn it over there first before, like I did with the other one, it's already got a dipole on it because obviously hydrogen and chlorine have different electronegativities. So this doesn't need to be polarized by this carbon-carbon double bond. So the dipole's this way around. Chlorine's more electronegative than hydrogen, and so we've got the delta plus on the hydrogen, the delta minus on the chlorine. So I'm just going to rattle through this mechanism now. Hopefully everything I said from the previous one will just still make sense, and we can just go through this one fairly quickly. Okay, so remember the pi electron pair will be attracted to the slightly positive atom. That's going to repel the pair of electrons in this bond, and it's going to break that bond by heterolytic fission. That's going to generate a carbocation. So I'm going to put the hydrogen on this carbon here, and that's got a positive charge on it. That chlorine, it's a negative charge. There's the pair of electrons that we're going to bring in to form that covalent bond. And so the final product would look like this. Okay, so we're still on with electrophilic addition, and we're still on with alkenes with hydrogen halide. But the point I want to make in this one is this is propane. This is an unsymmetrical alkene. So when you have an unsymmetrical alkene, there are actually two possible products when you react it with something like a hydrogen halide. So I'm going to show you both possible products and then explain which one will be formed in preference to the other one. So we'd call that the major product, and you would still get a little bit of the other one, so that's what we call the minor product. So I'm going to draw the propane in the middle, and then we're going to split for the two roots of the mechanism. So let's just put CH3 up there for that extra carbon. Okay. So HCl obviously is polar anyway. Delta plus on the hydrogen, delta minus on the chlorine. So same thing happens, you've got the pi electron pair, that's the sigma electron pair. Pi electron pair attracted to the slightly positive hydrogen, and the bond breaks by heterolytic fission. Okay, so two possible outcomes of that. So on this side of the board, let's put the hydrogen there on that carbon, and that's going to generate this carbocation. That one there. And obviously we've got a chloride ion produced as well. Or we could put the hydrogen on that carbon. So that means this first carbon is the one with the positive charge. Then we go to this carbon, so CH3, H, and there's that new H, that one there. And obviously we need the chloride ion, so we'll just draw it there. Okay, so the final part of the mechanism, I'm sure you can work it out, it's going to be that covalent bonds formed between that pair of electrons and that positive carbon, and likewise there. So there's the product of both of those curly arrows. So this one here is, we've got 1, 2, 3 carbons in the chain. So propane with the chlorine and carbon number 2, so that's 2 chloropropane. And this one here, 3 carbons in the chain, continuous chain, chlorine on the first one, so this is 1 chloropropane. So 2 possible products from that reaction. So what we need to focus on here is the carbocations. So this carbocation here, what I'm stood next to now, we need to establish whether it's a primary, a secondary, or a tertiary carbocation. So what we need to do is look at how many carbons are directly attached to the positive carbon. Okay, so there's your positive carbon. There's only 1 carbon directly attached to that. So this is what we call a primary. So I'm just going to use the 1 sort of degrees symbol. This is a primary carbocation. This one here, we've got a carbon with the plus on, we've got 1, 2 carbons directly attached. So this is a secondary carbocation. So what we need to ask now is which is the most stable of those 2 carbocations, and the answer is the secondary carbocation. carbocation. So the reason for that is the alkyl groups that are attached to this positive carbon, they have what's called an inductive effect, which means that they can release electron density and help spread the charge around the ion and basically help stabilize it. So the secondary carbocation is more stable than the primary carbocation because that's only got one alkyl group feeding the electron density in to stabilize the ion, and so therefore this is less stable. So because that's more stable, you get more of this product formed and less of this product. So your 2-chloropropane would be your major product, and your 1-chloropropane would be your minor product. I've just written up in the corner there, carbocation stability, tertiary carbocations, which we haven't got in this case, but a tertiary carbocation, so that's got 3 alkyl groups attached to the positive carbon, so that's more able to spread out that positive charge on the ion. If you can form a tertiary carbocation, that's going to be more stable again, okay? So tertiary carbocations are the most stable, then secondary, which we saw here, then primary, which we saw there. The next electrophilic addition mechanism we'll look at is the one between an alkene, so I'm using ethane in this case, and sulfuric acid. So I've already drawn the ethane and the sulfuric acid up. Look at how I've drawn the sulfuric acid. We're exaggerating this HO bond at the end of the molecule so we can show the dipole nice and clearly. So that hydrogen's slightly positive, that oxygen's slightly negative. And so basically you're going to see the same thing happening as before. So we'll just go through this fairly quickly now. Pair of electrons from the pi bond attracted to that hydrogen, slightly positive hydrogen. That's going to repel the electrons on this HO bond completely onto the oxygen. That's going to generate carbocation. And because this is symmetrical, it doesn't matter where I put the hydrogen, so I'm just going to put it on the first one. So we've got, there's your carbocation, and this will be OSO2OH with a minus charge. There's the pair of electrons, and we get that. The next electrophilic addition reaction we'll look at is the reaction between an alkene and steam, so gaseous H2O. You'll see I'm using ethene again as my alkene, and this reaction needs an H plus catalyst, and the acid we use, so that H plus comes from H3PO4. Okay, so there's the alkene, there's the H plus from the H3PO4, the phosphoric acid. So pair of electrons from the pi bond, make sure you go from the middle, is going to come out and form a covalent bond with the H plus. So I'll just put that on the first carbon. So that means this carbon here has 2 hydrogens attached, and it's also positively charged, so that's your carbocation. Remember, we've got H2O present, so I'm going to bring that into play now. Oxygen on H2O has 2 lone pairs. I'll show them both, but I only need to show one really. So hopefully you can see there's going to be an interaction between a pair of electrons and that carbon. So we get this. So we get another sort of intermediate formed. So we've got CH3, CH2, and then we've got this water molecule, but it's effectively lost an electron to that carbon. So this is now positively charged. And then what we're going to do is this stabilizes itself by losing this pair of electrons is donated to the oxygen. So we'll just show that like that. So that's a curly arrow from the middle of that OH bond onto the positively charged oxygen. So this H here is going to break off and will become an H plus ion. So go this way. And we get the H plus reformed, and therefore that's showing that the H plus ion is behaving as a catalyst. So if we move on to nucleophilic substitution mechanisms now. So the one we're looking at here is a haloalkane, so I'm using bromomethane as my example, and I'm using aqueous hydroxide ions. So I've drawn up the haloalkane and the hydroxide ion. Notice I'm showing the lone pair on the oxygen. So this carbon halogen bond has a dipole across it, so the carbon is slightly positive, the bromine is slightly negative. Nice simple mechanism, this one, so you can see hopefully that that pair of electrons will be attracted to that carbon, and that will break this bond by heterolytic fission, and what it'll do is it'll repel a pair of electrons in the bond completely onto that bromine there, and we get this product. So we get methanol, and obviously that bromine is going to become a bromide ion, and that's the mechanism there. The hydroxide ion is obviously acting as a nucleophile, hence the name nucleophilic, and that's because it's donating a pair of electrons. So nucleophile is an electron pair donor. So this hydroxide ion is behaving as the nucleophile. Substitution, obviously, because we've substituted bromine for a hydroxyl group, an OH group. The next nucleophilic substitution mechanism is between a haloalkane and a cyanide ion, Cn-. So the mechanism now, very similar to before. We've got a delta plus on that carbon, a delta minus on the bromine. The pair of electrons, the cyanide ion on the carbon, is attracted to this positive, slightly positive carbon, breaks the bond by heterolytic fission, and it generates this product. So CH3, we've got Cn there. This is what we call a nitrile. So this will be called ethanonitrile, and we get Br minus. Again, this is acting as a nucleophile because it's donating a pair of electrons. Substitution, because we've substituted bromine for a Cn group. The next nucleophilic substitution mechanism we're looking at is between a haloalkane and ammonia. So a little bit more to this one. So moving on to the mechanism, I've already populated the first part. So we've got the lone pair of electrons on the nitrogen of the ammonia attracted to that slightly positive carbon, and that breaks this carbon halogen bond by heterolytic fission. So that's going to generate this intermediate. So this nitrogen here, still got those three hydrogens attached, but effectively the nitrogen's it hasn't given away the electron to the carbon, but the carbon's kind of taken ownership of one of these electrons here. So the nitrogen has a positive charge on it. Obviously the bromine there, negatively charged, Br minus. Okay, so the next part of the mechanism, we need to bring another ammonia molecule into play. So what that's going to do is it's going to grab hold of, say, this hydrogen here, and the pair of electrons in this bond are going to go onto the nitrogen, and that's basically going to get rid of that positive charge. So if we look at what's going to be formed as an upshot of that, we've got the organic product CH3, and then we're going down to NH2 now. This is what we call an amine, so this is methyl amine. We've got an NH4 plus ion, and we've also got a Br minus ion. The last set of mechanisms now we're looking at are elimination mechanisms. So the first one we'll look at is the one with alcohols reacting with concentrated sulfuric acid or concentrated phosphoric acid. So for this example I'm using ethanol, and the H plus ion is being provided by one of these concentrated acids. So you can see we've got two lone pairs on the oxygen. One of them is going to form a covalent bond with the H plus ion, and that's going to generate this intermediate, and that oxygen's got a positive charge because it's effectively lost an electron to the H there, the H plus. The next thing to happen is this pair of electrons in this carbon-oxygen bond goes onto the oxygen to stabilise that positive charge. So effectively a water molecule breaks off, and what that's going to do is it's going to leave a positive charge on this carbon here, because that carbon's lost one of the electrons, its electron from the bond. And for this to stabilise itself, what needs to happen is we're going to get a pair of electrons from an adjacent carbon to the carbon with the positive charge. So let's go for this one. A pair of electrons here, they're going to move into there and they're going to create a carbon-carbon double bond. And this is obviously going to break off as an H plus ion. The last elimination mechanism we'll look at is the one with haloalkanes with ethanolic hydroxide ions. So that's basically sodium hydroxide but dissolved in ethanol. So for the purpose of the mechanism I'm using bromoethane and hydroxide ions obviously. You see I've already put the dipole across the carbon-halogen bond. So what happens here is a pair of electrons from the hydroxide ion, or the oxygen, is drawn towards a hydrogen on a carbon adjacent to the slightly positive carbon. What that's going to do is it's going to repel a pair of electrons from this carbon-hydrogen bond onto this carbon-carbon bond. That's going to generate a double bond there. And then what we need to do is the electron pair in this bond will be repelled onto that bromine, and this will be broken, this bond is broken by heterolytic fission. And so the result of all of that, well, that's going to become a water molecule. This is going to become, in this case it'll be ethene, because we've got a double bond between the two carbons. And this will be a bromide ion, Br minus.